with the help of a console, and the session was great. Only thing is that okay, I have worked on that domain, so for me it was okay. But those who are working for the first time, maybe for them, speed is a little. Basically, we are concentrating one domain on one actually. This
Mm-hmm.
one session only. So maybe if it is divided into multiple session actually for one domain,
Mm-hmm.
one application, then it would be little easier actually for everyone. Those who are working for the
Okay,
first time. Okay, I have not
I
worked for this
understand.
one, so for me it is okay.
Yeah, I understand. I agree on that. Stuti, are you all working on piezoelectric? I'm not sure.
No, ma'am. We are not
Yes, ma'am.
working on the capacitive-based sensors basically. So that will be covered in this training.
Yes, yes. No, no.
So
Yeah,
I,
yeah. That is covered on that one. I worked on piezoelectric cantilevers. That's why for me it is
ah,
easy to understand the flow.
mhm. So,
I have
Suti,
designed
what
the
I would say is
cantilever.
that in one session, just you choose one example. If you're doing a pressure
Okay.
sensor, just do one pressure sensor. Don't do multiple. People
Okay.
might not be able to follow who are first timers. Might be at the end or when we are hand holding them for design submission next year. That time
Yes,
you
ma'am.
can go a little fast, but at the beginning, just do one in one session so
Sure,
that
ma'am.
everyone is in the same pace.
Yes, ma'am.
And also, those who are in Bangalore, you all can visit NMIT and talk to them, discuss with them, and that will help more to be there physically and interact. In fact, I was a faculty in NMIT for 17 years before I moved to Ireland. And this activity we have done for last 15 years in India. And even undergrad students ended up doing such wonderful work that it was better than any PhD student who could give designs. That is what inspired me when I came to Ireland and I got the opportunity to, through the Sensors Council, to make this a global activity. And now I see people from Africa, people from Brazil, people from even Ivy League schools in US. Believe me, they are also getting trained. There are people from Purdue, from UC Berkeley, from Caltech, also part of this training, which is amazing. So it's not just that underprivileged nations are participating, even the nations which are having all the infrastructure are part of this training. So make best use of it is what I would say. You won't get this chance again and again. Any other feedback? If not, what I would say is that in the coming weeks, I'll be having a meeting with all the chapter chairs and with all the nodal centers, and we will be dividing you people into different groups so that and the groups need not be within yourself for attending. The groups could be across the other nodal centers so that you all start talking to each other, you all start interacting, and the design submission will happen one design per group. So there will be one person from, say, Africa, one person, say, from southern India, one person, let's say, from Bangladesh or somewhere else, one person from US. So we'll mix and match all of you, and that each design will be then a real, true global design, and each design will be very unique in its own way. I hope you all are okay with that. Any suggestions on what you think how the group should function? All of you all are learning the same thing. All the nodal centers are following the same pattern, the same method of teaching. It's the same flow. So y'all will not be left deserted, and each team will have one or the other as a mentor to handhold you and for your design submission. And in each team, there will be a few people who understand MEMS and the SOI process, and many others for whom MEMS is new. So you won't be left in the dark that, oh, how do I go about it? You will be in safe hands is what I want to say. But we want to make y'all collaborate across institutes, across nations, across continents. That collaborative spirit is very important. And this gives you that platform to collaborate people across the globe. The idea is that eventually when these devices get fabricated and they come over and you test them, and let's say, by all luck that we have, and if the designs are doing well, if the devices are functioning exactly like or almost as designed, And if you'll have publications, in that publication, you will have authors from different nationalities, from different continents, from different institutes. That's the wonderful part of being very collaborative in your spirit. Any suggestion on what I said just now on making groups? So your silence means you all are accepting. So that's great. Today afternoon, my time afternoon, your night 8:30 in India, my time 3 o'clock. We are having the second webinar in the series of webinars that I'm doing. Please do attend it at your 8:30. I think all of you have received the Zoom link for it. In this webinar, what we will be talking about is exactly what we mean by MPW, run. What is a multi-process wafer run, how it works, and also tell you about different MPW runs that the Science Foundry does. Science is a foundry in US where we are going to submit these designs. They don't have just one type of MPW run, they have different types. And the director lead of the foundry will be also one of the speakers. So please do attend that and understand what you're going to be learning. That's happening at 8:30 today. The next will be on 14th of November. There we will be going in detail about the SOI design rules. That is exactly the design rules that you will be using for submitting the designs for fabrication next year. And that's the design rules that the team from NMIT is going to teach you while you are designing and simulating. You have to follow strictly those design rules. So that will be on 14th of November. And then on 22nd November, we'll have one more webinar on industry application of MEMS. So one expert from Robert Bosch in Germany and one expert from Texas Instrument based in US Kilby Labs. They will be the speakers. So they will talk of different aspects of MEMS, right from inertial sensors in automotive applications, which Robert Bosch is very good at, to RF MEMS using piezoelectric devices from Texas Instruments will also be touched upon. So do attend these webinars. And then in December, I'll have the final webinar on testing and characterization of MEMS devices. So though I said in the beginning that we won't help you with testing and we will not be paying for your testing, what we will do is actually help you understand where you can go and test your devices. Especially in India, it's not difficult at all. There is IAC, there is IIT Bombay, there are all these premier institutions who do it. Also, BITS Pilani Hyderabad campus has a very good facility and they have come forward to help as well. So we have many options for you, and please do attend these webinars in parallel to your training sessions. If you are for some reason you cannot attend it, at least please view the recording of these webinars and training sessions. So that's all I wanted to say. Stuti, please go ahead and continue your training. And anytime any one of you can email me, I'm there to help.
Yes,
Excuse me,
thank
ma'am.
Yes, tell me.
Ma'am, whether this webinars will be available in YouTube, madam?
Yes, after the
Okay.
webinar,
Yes.
the recording will be available on IEEE Sensors Council YouTube.
Okay.
The first one is already there. You can
Okay.
view it. The second one also will be available.
Okay.
Okay, Stuti, you can continue.
Yes, ma'am. Thank you. With your permission, uh, let me start today's session. Uh, I will share the screen. Is it visible to you? Is the screen visible?
Yes, ma'am. Yes, ma'am. Yes,
Yes.
ma'am.
Okay. Thank you. Okay. As ma'am said, so we will be dealing with the capacitive based sensor as one of the major sensor which can be used with the help of a SOI process flow. So with that, we'll be dealing with how exactly we can design a MEMS accelerometer as a part of this entire training session. So before which we have started with giving the basic introduction about how to start the design process. So we started with the designing the MEMS cantilever beam as a first step, and today we will be dealing with how exactly we can use a COMSOL multiphysics tool to design and extract the information. Basically, MEMS is micro electromechanical system where we have mechanical structures giving out the electrical output in the form of a capacitance, if it is a piezoelectric in terms of a voltage, if it is a piezoresistive in terms of a resistor. So today, as I mentioned, we will be dealing with the MEMS capacitive sensor. So the foundation of which is the physics called as the electromechanical physics. So I will be taking you through few basic concepts on the design aspects, and also a flow on how we design the MEMS capacitive sensor in the COMSOL. So going ahead, this is the topic for today's session. So I'll be taking a simple example before I start, which is basically a MEMS capacitive pressure sensor. We can see here in this pressure sensor, we have a silicon membrane and we have a metal electrode, which is a gold, which can be used to detect the distance between the silicon membrane and the gold, which will be then converted into the equivalent capacitance. So basically, the concept called as the parallel plate capacitance is important in the pressure sensor. We can see here we have a silicon membrane and we have a metal electrode. So basically these two form a parallel plate capacitance, and in the structure B, what we can see is there is a membrane which is deformed. So when we apply some external pressure, this membrane is deformed, and because of which we can see that there is a change in the gap between the silicon membrane and the metal electrode. So by this we can measure what is the change in the capacitance, and then it can be converted into equivalent voltage. That is how we measure the pressure into the equivalent capacitance and then into the equivalent electrical values. So we can see that here we have two conductive plates. One is silicon, the other one is the gold material. So here the change in the distance between the conductive plates is converted into the change in the capacitance value, which is then converted into the electrical signal depending on the applied pressure. Okay, so with the help of a simple pressure sensor, now the concept of how exactly we can apply the simple parallel plate capacitance as a pressure sensor, so that we will be looking at. So we can see that we have a simple parallel plate capacitance. We all know that a capacitor is basically a storage element which stores the electrical energy, which consists of basically two plates, parallel plates separated by a distance. Okay, when we apply a certain voltage across this plate, the electrical charges, basically the positive charges, will be accumulated on one plate and the negative charges will be deposited on the other plate, right? So when we know that the simple basic equation, which is equal to C, which is equal to epsilon A by D, wherein epsilon is the permittivity of the dielectric material and A is the area of the two plates which are facing each other, and D is the distance between them. So here we can see few equations that says how exactly we got the capacitance equation to be epsilon A by D. So we know that we have a parallel plate capacitance wherein the amount of the capacitance is inversely proportional to the distance between the plates. Okay, so in this parallel plate, since we can say that the distance between the plates is very much smaller compared to the area of the plates, okay, then the electric field generated by them can be treated as equal to the electric field that is generated by infinite plane sheet of uniform surface charge density. So this concept we have studied in the physics, where this electric field generated can be equivalent to how exactly the electric field generated by when we have a infinite plane sheet. Okay, and this is based on the surface charge density, that is basically the Q that is present here. So we know that the surface charge density, which is sigma here, is given by Q by A, where Q is the number of charges that is accumulated on the plates and area is the A is the area of the parallel plate. So if we want to calculate the effective electric field, then the electric field due to this charge separation and the charge carriers are given by the charge density sigma by the epsilon, that is a permittivity of the medium, and the potential difference between the plate is given by the V is equal to the electric field into the distance. From these two basic equations, that is the surface charge density equation and the electric field that is generated by those surface charges, we calculate what is the electric potential that is present between the plates, which is given by E into D. And from these two equations, we can equate for the charge carriers, that is sigma. And finally, we get the C, which is nothing but the capacitance value, which is given by Q by V, where Q is the epsilon, Q by is the charge, number of charges that is accumulated on the parallel plate, and V is the potential difference between the plates. So we know that a simple parallel plate capacitor can be used to store the charges, right? And with the help of charges, we develop some electric field and the potential across these plates. So going to the next step, plates, that is that can be classified as two categories. One is the normal force, the other one is the transverse force. So we will look into the normal force, what are the parameters and how exactly the normal force come into the picture. Okay, so we know that the work done or the energy stored by the capacitor is given by half into CV square. Okay, so if I have to calculate the net force that is acting upon the parallel plate, then it is the amount of the work done over the distance d. Okay, so force I can relate with the work done equation, that is half CV square. When I substitute, I get the net effective force, which is the normal force acting between the plates, is given by epsilon A V square by 2D square, where A is the area of the plates, epsilon is the permittivity of the medium, V is the potential difference between the plates, and D is the gap between the two plates. So this is the electrostatic force that is acting between the two parallel plates. So keeping this in mind, let us move ahead. So the concept of how exactly we can apply the simple parallel plate capacitance in the sensor application basically. So I have taken an example wherein there is a kind of mass which is suspended, or diaphragm which is suspended through a spring here, which is attached to a contact. So the blue color ones are the contacts which are fixed, and the mass is fixed to these contacts through a simple spring mechanism. And on the bottom we have one more fixed plate, which is basically to measure the distance, the variation between the concept of parallel plate capacitance. So we are going to apply this concept to the concept of parallel plate capacitance, wherein we have the bottom plate as a fixed plate and one more plate which is on the top as the movable plate, and this movement is controlled by the spring action through the springs or the connecting rods which is connecting the or holding the mass. Okay, so we consider here A is one proof mass and B is the substrate, or wherein we can coat with some electrode material to sense the variation in the capacitance. And I assume that there is a distance d between the two different plates. One is fixed plate, the other one is the movable plate. Okay, so when I exert a force, so let us come to the second picture. When I exert a force, then the proof mass would deflect. Okay, and what we can see here is the distance is initially it was d, now the distance is reduced to d minus y, where y is the displacement of the proof mass by the for the external force. Okay, so we can see there is a deflection here, and we can see the gap has been reduced from d to d minus y. So from the concept of parallel plate capacitance, we know that whenever the distance varies, the capacitance also varies. So by knowing the variation in the capacitance, we can measure what is the external pressure that has been applied on the mass or the diaphragm. Okay, so let me consider a few more concepts relative to this. So what we have understood is that when we have a proof mass or a diaphragm which is suspended through some contacts, okay, when it is exerted with external force or a pressure, it deflects, and when it deflects, the gap between the plates will reduce, and because of which the capacitance value will change, right? So in this mechanism, there are two forces that is acting upon. One is the elastic force given by the Hooke's law. You can see here F is equal to, which is nothing but the mechanical elastic force Fm is equal to minus k into y. One is this force, the elastic force. The other one is the electrostatic force, which is given by Fe is equal to epsilon a v square by 2d. Initially it is 2d square, but now because of the displacement we can see that the d has been reduced by a factor of d minus y the whole square. Okay, so when we consider this, there are two forces which are coming into the picture. Okay, one is the elastic force given by Hooke's law, which says that the amount of the displacement is directly proportional to the force that has been applied with the constant given by the spring constant k, right? And the other one is the electrostatic force, which varies as the gap between the two electrodes varies, right? D minus y the whole square. Okay, so if we have to operate, right, in a uniform way, wherein only when the pressure applies there should be deflection and there should be capacitance change, and there should be some electrical output which is taken from this capacitance change, right? So if this has to function in a good way, okay, without disturbing the structure, right, then we have to ensure that the mechanical force, that is the elastic force, should be equal to the electrostatic force. Okay, so at equilibrium we expect the mechanical force, that is elastic force, to be equal to the electrostatic force. Okay, so as I mentioned, this is my electrostatic force and this is my elastic force. I represent by Fm so that there will be a difference between the two forces. So there will be a net force that is acting upon. So we have the elastic force because of the spring and the movement of the diaphragm, and we have the electrostatic force because we have to extract the information in the form of capacitance. So we need to apply some voltage across the fixed and movable plates. So that develops the electrostatic force given by Fe. So we say that the total resultant force that should be less than zero, right? Let us think or understand why, right? So we say that from the equations we know that half the previous, from the previous equations, this is the equation, right? Epsilon av square by 2 d minus y the whole square is the electrostatic force. So I consider that here, okay, minus the mechanical force, which is given by k into y, should be less than 0. Okay, so if I take the derivative of the relative force with respect to the displacement, how exactly the force and displacement are related, okay, then I can consider that the derivative, the first derivative of this resultant force should, with respect to the variation, the displacement should be less than 0, which says that it should be a negative value. Okay, so I consider this, the next equation, the same continuation of that is, I substitute epsilon av square d minus y. I take the derivative of this first function, right? So what I get, epsilon av square by d minus y the whole square into, we can say that d minus y the whole square is a function of y, right? So I can write the derivative of that function to be 1 by d minus y, basically 2 by d minus y. So that the particular 2 and this 2 will get cancelled, and we get epsilon av square by d minus y the whole square into 1 by d minus y minus k should be less than 0. Okay, then from these two equations, what I can consider is this can be rewritten as, from this equation, I can write it as 2 into, so epsilon a v square d minus y the whole square. I have epsilon a v square by d minus y the whole square. This can be written as, I take the 2 here, so 2 into ky, right? So I can write this entire term to be 2 times the stiffness and the displacement, okay? And the rest of the values remains the same, so 1 by d minus y minus k. So I can write 2 into ky divided by d minus y as it is minus k should be less than 0, okay? And when I relate, okay, finally I get the value of y, which is nothing but the displacement of the mass, okay, should be less than or equal to the distance between the plates by 3, okay. So here we can see that the maximum displacement should be always less than the distance between the plate by amount of 1 by 3. The reason is there is something called as pull-in voltage or pull-in effect that is coming into the picture. So let us understand what is that pull-in voltage. Okay. So by this relation, so I have two forces that is acting upon. One is the elastic force, the other one is the electrostatic force, right? So I have the elastic force here and I have the electrostatic force. So in this case, if I consider, if I have to plot the force versus the displacement, how exactly the force and displacements are in related with respect to these equations, what I get is, if I consider the elastic force, right, I can see the displacement is varying in linear with the force applied. So I can see, you can see this blue color line. So as the force is increased, the displacement is also increasing, right? Next, let me consider another equation which is relevant to the electrostatic force that is acting between the plates, which is given by Fe is equal to epsilon Av square divided by 2 minus d minus the y the whole square. We can say that here the y displacement is proportional to the applied force in the parabolic form. So I get the one which is in red color as the response to the electrostatic force that is acting between the plates. Okay. So in this case, now I see I have noted 2 points. One is A, the other one is B. Okay. So in this point A, okay, I can say that after the point A, right? After till this point, it's fine. But after A, okay, when I move ahead with the force, the elastic force is increasing linearly, right? Whereas the electrostatic force is reducing. That means the force of attraction between the plates are less compared to the elastic force, right? So we have an elastic force which is predominant than the electrostatic force. So if I apply the pressure and it will deflect, and when I remove the pressure, it will come back to its original position. That is, it is elastic in nature. So there is no problem because the electrostatic force is negligible compared to that of the elastic force. So elastic force is more predominant than the electrostatic force. Okay. But after this point, wherein I reach a point B, I see that the elastic force is increasing linearly, whereas I see there is a sudden drift of the electrostatic force. Electrostatic force is going in the steeper direction, right? More steeper, right? In this case, what happens? Electrostatic force is higher than the elastic force, right? So when I come to this, right, this elastic force, right, here I have two forces. One is electrostatic force. The other one is because of the spring motion, that is elastic force, right? When I insert a pressure, right, like this, I insert a pressure, right, it will deflect. When I remove the pressure, it will come back to the original position like this. But when I have the electrostatic force, which is more stronger than the elastic force, then what happens? This entire plate will be pulled in by the bottom plate, and we see that this is completely going and touching the bottom plate, and after which it is not possible by the elastic force to bring it back to the original position. Okay, so this concept is called as pull-in voltage, right? In order to avoid the pull-in voltage, we need to make sure that the displacement, okay, by this two plates should be less than the distance by a factor of 3. Okay, so this is more important. When we are designing some capacitive based sensor, we should keep in mind of this elastic force and the electrostatic force which is acting between the plates. Okay, and we should ensure that the maximum amount of the displacement should always be less than the distance between the plates by a factor of 3. So for example, when you are designing a pressure sensor of up to, let us consider 10 Pascal, okay, and the distance you've kept it as, for example, I'm just taking one random example, 1 micrometer, okay. So this is the distance between the two plates, okay, and when I keep changing the pressure, let us consider it is moving, the displacement is too slow in the case of maybe in terms of a nanometer, but if I apply certain pressure wherein I get 1.2 micrometer as the displacement, okay, then I I feel there is more of electrostatic force which is more predominant than the elastic force, then I cannot use that particular structure once again for sensing. I hope that is clear to you. So this is known as the pull-in mechanism. So we have to be very much cautious about deciding the distance between the plates, or if in the case of pressure sensor or in the case of any capacitive sensor that we are going ahead with the design, we should be sure that the maximum displacement cannot overcome the distance between the plate, otherwise it will cause a pull-in effect, and the voltage at which the pull-in effect uh, comes into picture is dependent on the factor which is given by the pull-in voltage is 8 into the stiffness K into the distance between the plates, the cube of the distance, divided by 27 into epsilon A, epsilon E, epsilon, it can be relative permittivity as well as the absolute permittivity. So I've considered just as epsilon, and then the area between the plates. So for any design, we need to make sure two things. One is never the electrostatic force should be greater than the elastic force that is acting on the sensor, okay. And one more thing, to ensure that I have to calculate based on my stiffness, based on the area of the plate, I can calculate what is the effective voltage at which this pull-in effect is dominant, and what is the maximum displacement I can keep between the plates such that the pull-in effect I can be eliminated from my design. Okay, so this is one more concept of pull-in voltage. Next comes the transverse force, right? So if I have to design some actuation is basically movement, right? Movement between the plates. So either what I can consider is the simple parallel plate capacitance I can actuate, and which can be used as one of the application is in the form of a gyroscope, wherein I need to keep the electrostatic action in live to detect the change in the angles. Okay, so here what I see here is the same parallel plate with the gap D, right? But only changes, instead of moving up and down, it is moving in the horizontal direction as in the form of X, right? So we can see I have represented here the top plate is moving in plane movement along with the bottom fixed plate, such that the transverse force, right, of these capacitance, parallel plate capacitance is given by, similar to the previous equation, we have F is equal to the work done by the distance CV square by 2D, but here whatever the value of the capacitance is different. Okay, so we know that in this case the amount of the work done, which is dependent on the C and V, right, here the equation for the C is different. So here I can see, so this is the equation for C, where instead of A I write it as B, that is the breadth of the moving plate which are facing each other, right? What is the total breadth from here to here? What is the breadth of the parallel plate which is moving along the X direction, and what is the distance of overlap? So from here to here, from this point, right, till this point, there is a overlapping area. So I have to consider this X and this breadth as the overlapping area. So I write work done is equal to half into B, which is a breadth of the parallel plate, into the overlapping distance X epsilon by D. Okay, so in this case, if I have to find out the effective force that is acting, then if I take the derivative of this force with respect to the displacement X, I get the transverse force to be equal to B, because I'm taking change in the force with respect to change over the distance X here. Okay, the resultant force, right, which is given by change in the force in the lateral direction divided by the change in the distance, which is nothing but X. Here I get the Ft is equal to B, which is the overlapping breadth into the permittivity and the voltage that has been applied on the plates divided by the gap. See here, the gap is going to remain fixed. Okay, and we can say that the breadth is also, right, same, it is not changing, only we see that distance is changing and it has no much effect on the transverse force. Okay, so in the vertical direction, there is a pull-in effect which has to be considered, whereas in the case of transverse force, we can say that it is independent of the lateral direction movement X. Okay, so this concept, as I said, can be used for the electrostatic actuation. So we can design the combs such that if without considering, or we can say that without making sure that pull-in voltage is not affecting, we can carefully design the voltage that can be applied to it so that we get the maximum displacement and hence between the electrostatic actuation, so that we can get the better actuation or the displacement by applying the voltage. So we should know what is that voltage. Okay, first we need to find out what is the pull-in voltage. Okay, so that we avoid that voltage, and then we design how exactly this actuation can be varied with respect to the applied voltage through the equations that we have done so far. Okay, so with this, one of the simplest example or the application what we have seen here is the variable capacitance. So we have already seen a MEMS pressure sensor which can be used to detect the pressure. The other application could be in development of the variable capacitive sensor. We can see here. So you apply the voltage between these plates here like this. Okay, so you change the displacement, or you change the distance between these, right? So you can change the distance between these electrodes by applying the external voltage, and as the distance varies, right, so we apply the voltage, we get the displacement, and as the displacement, as the distance between these two changes, these two gaps changes, then the capacitance will change, because the capacitance is inversely proportional to the distance between them, right? And once we measure the capacitance, then we can find out what is the relationship between the voltage to the capacitance. So that is how we can use this concept to build a simple variable capacitor. So as we change the voltage, the capacitor value will change. Okay, So this is basic idea you need to understand in terms of using capacitive sensing. Okay, one point to remember is that you have to design the gap between the electrodes or gap between the two parallel plates carefully, such that you avoid pulling voltage. Okay, and one more thing is, you can use this voltage to actuate the electrode, so that you can use the concept of a parallel plate capacitor as the actuation mechanism. So it can be used as a sensor, and also it can be used as a actuator. Okay, any doubt? Any doubt?
No, madam.
Okay, so please remember two things. So when you are designing the capacitive sensor, okay, the important thing is what is the minimum distance that you keep between the plates, so that you avoid the pull-in effect. Okay, so you can design it carefully, right? And these are the few equations which will help you in designing the MEMS capacitive sensors. Basically, the mechanical elastic force, which is given by Fm, and the other one is the electrostatic force. Okay, so you can directly measure the change in the capacitance over the change in the distance between the plates. But make sure whenever you keep the distances between the plates, it is such that it will not fall into the pull-in voltage effect or pull-in effect between the two different parallel plates. Okay, so these are the equations. Let me just rush through this once again. So a concept of a parallel plate capacitance, which is applied on the pressure sensor, okay, wherein we have a membrane which deforms for the external pressure, and by measuring the change in the distance between the membrane and the electrodes, we can find out what is the applied pressure, right? And then the concept of electrostatic force, we know that when we have two different parallel plates, two conductive plates connected together, or we can say brought in together with the certain separation d, will act as storing the storage element which can store the charges by applying the external voltage. Okay, when we apply the voltage, so there are charges accumulated on these plates. As the charges accumulate, it creates an electric field between the two plates, and this electric field will develop the potential difference between the plates, and that is given by V is equal to the field into the distance and the capacity, how much the plates can store the charge. It depends on the voltage that is applied and the capacitance or the capability of these materials to store the charges. And from this directly we can say that the capacitance, the amount of charges that can be accumulated on the plates, are directly proportional to the area of the plate and what is the separation between the two plates, right? And from this we can say that we cannot change the area much, right, because it has direct relation. But if we change the distance, because it is in the micrometer scale, a small change in the distance can cause a lot of change, or a good change in the capacitance value, right? So we apply this concept in the pressure sensor, right? So when we consider the concept of a parallel plate in the parallel pressure sensor, we need to make sure of two forces that is acting. One is the electrostatic force, that is the normal force. The other one is the transverse force. So transverse force, we don't have to worry much, because it is basically used in the actuation mechanism most of the time, and it is dependent on what is the applied force. The displacement will not, we can effectively control the displacement along the lateral direction by knowing what is the pull-in voltage. And if it is a pressure sensor, wherein it is most important, we should be keeping a note on what is the pull-in voltage, and what should be the minimum distance I should keep between the electrodes, so that I avoid this pull-in effect coming into the picture. So in order to do that, we have considered that, right? We have considered one example wherein I have a proof mass which is separated by a distance with the help of and we have a fixed plate here bottom. The contact blue color ones are the fixed plates, okay. And this is a proof mass which is a free to move, suspended by the beams, right? So when we apply certain pressure, we see that it will deflect by amount y. We have considered a certain variable as y is the displacement, and as y varies, we see that the electrostatic force will vary by a larger amount, okay. And in order to function, in order to enable this pressure sensor to function as our requirement, that is, it should be very much sensible to the external pressure, and it should not it should be flexible, that it should descend and come back to its original position, right? It should not give some random values, or it should not stick to the bottom plate, right? And that concept is known as the electrostatic the pull-in voltage, which is because of the electrostatic force. We say that for a pressure sensor to work effectively, okay, the deflection should be elastic in nature, right? And the diaphragm should be free to move back to its position once the pressure is removed. But if the displacement is too much larger, then we can say that the electrostatic force is much higher than the elastic force, and there is a concept called as pull in, the which will pull the diaphragm to the bottom plate, and it will get stuck. So any further force cannot return its position back to its original position, right? So this is the pull-in effect, okay. And we should find out what is the minimum gap that we can keep so that I can avoid the pull-in effect, which is given by the maximum displacement between the plates should always be less than the distance between the plates by a factor of 1 by 3. Okay, so when we design, this is one more important criteria to remember. The displacement should always be less than the distance by a factor of 3. Okay, and the deflection at which we can say that the pull-in voltage is effective, okay, that voltage is given by the root of these variables, that is the stiffness, the gap between them, the area, and the permittivity epsilon. So you can identify when you are designing a sensor, you can identify, because you would have designed for a particular frequency, so you would know what is the stiffness, and if you would know what is the distance between the plates that you can keep as your requirement, so that you have a better sensitivity, right? Then you can find out what is the pull-in voltage, so that you can avoid it during the functionality of the sensor and also the actuator. Okay, please keep these two things in your mind. Okay, so one more application is the MEMS cantilever beam, the variable capacitor with the help of external applied voltage between these electrodes, which can vary the distance between the electrodes. So by varying the distance, we know that the capacitance will change, and that's how we can relate directly the capacitance change with respect to the voltage change. Okay, with this, let us simulate a simple parallel plate capacitor in the COMSOL multiphysics. Okay, I have done the simulation. So this is what is the expected simulation. So I will take you through all the steps of this simulation, wherein I simulate the parallel plate capacitance, okay, and I find out what is the capacitance between the change when we apply certain pressure, how exactly it changes, and I can identify what is the displacement, and I can also identify what is the change in the capacitance between the parallel plates. So is it visible to all of you? Is
Yes,
the
madam.
screen? Yes. Okay. I'll just take you through the flow of simulating a simple parallel plate capacitor. Okay. So I'll take a model wizard. So as I said, it is a three-dimensional structure. So I will take a 3D Then, so we know that there are two concepts. One is the electronics concept, which is the electrostatics, right? The other one is the mechanical concept, right? Solid mechanics. So we can say there are two physics which are important in designing the capacitive sensor. Okay, so these two physics are combinedly present under structural mechanics as electromechanics. So you can see there are two electromechanics. Make sure you take the electromechanics wherein you combine solid mechanics with the electrostatics with the moving meshes. So there is a displacement, and that displacement is captured by the change in the capacitance. Okay, so take this electromechanics physics, add it. Okay, then we have to go for a study. So see, sensor, basically I do a stationary study, whereas in the case of actuator, I go with the time dependent study. Okay, so since we are now dealing with the sensor, I'll be going with the stationary study wherein static pressure is measured. Okay, so I will take a stationary study. Okay, this is my GUI. So first and foremost work is to change the length unit to micrometer. Okay, and so as I said, there are two methods of developing the structure. So one way is going directly through the block. So I'm taking a block. So I'm basically developing a parallel plate. So width is 100, depth is 100, and I'm taking a height of 5 micrometers. So if I have to observe, this is my XZ plane, right? So I'm taking height of, since you can take depending on the thickness of the material. So if the process gave 10 micrometer as the thickness of the silicon, then you can keep as 10. Okay, so I'm just building the structure. So this is one plate. I consider it to be bottom plate. Then what I do, I take one more block as the top plates. So one way is I can take this directly as a block. The other way is to duplicate this. So what I do, I right click, duplicate, and I change. So this the dimensions are same. Okay, only thing is I have to work with the position. So I change the Z parameter to be 20, which says that from here to here, I have 10 micrometer thickness electrode, one parallel plate, and I need to have another gap of 10 micrometer over which I need to have one more parallel plate. So I get this. You can see here, there is a measurement unit also, right? So we see this is 0, this position is 10. With the gap of 10, I have kept one more parallel plate, and this is the another parallel plate. One way is this. Okay, you want me to show the other way with the plane geometry? Anybody?
No, madam.
Yes, ma'am.
Okay, okay. What I'll do, I'll just delete this. Okay, one is this way where I can directly take the block. The other way is I'm taking a work plane. Okay, plane geometry, and I'm building a square. Let me, because it is basically a square, right? So I'm building a square. Okay, and then see, I need to have two plates separated, right? So what I have to do is I have to take one more work plane for one more electrode. See, you can, I'll just zoom in here. See, I have one work plane. Okay, I have one work plane, and I am taking one more work plane, and it should be how much distance away from the first work plane? Can anyone tell? So we have done with the help of block. We saw that I have one block which is 10 micrometer thickness. Then I gave a gap of 10 micrometer and I do another block, right? I duplicated and gave the distance between them as 20. Now, when I'm using work plane, this work plane is for the bottom plate, which has the thickness of 10 micrometer. Then what could be the work plane 2's position? Where exactly it should lie, on the x direction or the z direction? Can anyone tell where the work plane 2 should start? Because on the z direction, I need to keep one more parallel plate. I have one parallel plate, right? I need to keep one more on the top, separated by a distance of 10 micrometer. And I have the thickness of 10 micrometer for the bottom plate. So I will be extruding that. So what should be the z coordinate here?
10 micrometer.
10. And I need to have one more gap between the plates as 10. So 10 plus 10 will be 20. So I will be keeping one more work plane at a gap of 20. Okay. Now, what I do here in this work plane, I take another square, right, of 100 micrometer, and I have now two plates, but I have not defined the thickness. So how do I define the thickness? I go to the work plane and then what I do? I click on the extrude option. What is the thickness? 10, correct? So I'm giving a 10 micrometer. So bottom plate is ready. Next, I have to go for the work plane 2. What should be the thickness here? Again, 10. So this is another way of developing the structure. One way you can take directly this two blocks. Okay. The other way is you can take the work plate and give the thickness with the help of extrude option. Okay. Now, what are the constraints for a simple pressure sensor? What we have seen here, we are going to apply a pressure on the top plate, and top plates are fixed, yes or no, on the two sides as per our diagram, and the bottom plate is fixed. Okay, so let us assume the same conditions wherein I have to apply the boundary conditions, right? So before that, what is the next step? I have to apply the materials, right? So which material? So it is basically a silicon. So I apply a silicon to both of this, right? And then what I do is I go to solid mechanics. I apply the same boundary conditions. So what are the two boundary conditions under solid mechanics? Can anyone tell? Simple two boundary condition. You have done the micro cantilever beam, right? So similar to that, what are the boundary conditions? Even here, one is the fixed end.
One is
And
stationary, one is
yes,
movable, madam.
correct. One where we are applying the bound load, the other one is fixed, right? So I'll be taking the same two options, that is under the solid mechanics, I'm applying the load on the top surface and I assume it to be a pressure. So I'll apply a number. So it is dependent on your design. Okay, again. So I'm just assuming a 1 Pascal pressure is applied on the top surface. Okay. Next one is the fixed constraint. Okay. So basically this will be fixed through some beams, right? So we have seen simple beams, but again, as per your design requirement, you are going to fix the sides, okay, with the help of some springs. Okay, so as of now, I assume that these are fixed. Okay, it's basically diaphragm which should deflect at the center. That is why I apply the pressure on the top surface and all the sides are fixed. Okay, then coming to the electrostatics. So what we apply basically for the charges to accumulate? Can anyone tell? we apply the electric voltage potential between the plates, right? We apply the voltage between the plates so that there is a charge that is accumulated, right? And we can calculate the capacitance. So under the electrostatic force, electrostatic physics, we should apply two voltage, that is, one is ground. Okay, so always the fixed plate is taken to be a ground. Okay, and we take the voltage in terms of a terminal, the terminal voltage we apply to the top surface, right? So this is ground, this is voltage. What is the voltage? I just apply as of now 1. As I mentioned earlier, we should keep a track of pull-in voltage so that we avoid the electrostatic force overriding the elastic force. Okay. So now I have applied the ground and the terminal under the electrostatic physics, and I have applied the load and the fixed constant under the solid mechanics physics. Okay. Now, the next step is to mesh and then go for the study. Okay. So we can see that since all the sides are fixed, we see the maximum displacement in the center, which is given by about approximately 9 into 10 to the power of minus 9 micrometer, too small, right? This unit has to be considered as well as this. So it is somewhere around 9 into 10 to the power minus 9 micrometer. So again, this is a design criteria wherein you design the springs such that you get the better displacement. Okay. Now, let us find out what is the capacitance. See, this is the potential that we have applied. It is seen here. 1 volt to the top surface and 0 volt we have applied. Now we need to identify what is the capacitance. So for that, what I have to do is under the electric potential, I go to the multi-slice. From the solution 1, I take the data set. Expression is for, what are we trying to find out? The capacitance. And the capacitance has to be found under the physics electrostatics. So I go to the electrostatics. Okay, then I go to the terminals because under the terminals I have applied the voltage and I see what is the capacitance. So what is the capacitance? About minus 2.62 into 10 to the power minus 42, right? Minus 42 is too large. Can anyone tell the reason why it is minus 42? What have forgotten here or what have not considered here? Anyone can just tell what is the parameter I have not considered here because of which I am getting the capacitance as 10 to the power of minus 42. Anyone?
Dielectric constant.
Very good. It's a dielectric. Yes, good. So it's the dielectric medium. We have not considered any dielectric medium, right? So what we have to do is, in general, what is the dielectric medium that we use in general? Air, correct? So we have to now enclose this plate within the air block. So what do we do for that? I take my geometry, I go for a block. Okay, so I position the block such that these parallel plates are coming exactly the center. So I give about 300 depth, 300 and height of about 50. I position it such that this is coming at the center. Okay, the two plates are coming at the center. Minus 50 and Z I keep around minus 10. Okay, but it is not visible to me, right? So I have option here to see the internal objects. See here, this can be chosen to see how exactly the internal structure is present. Okay, this is too bigger, so I, instead of it will take a lot of time to simulate, so I've taken, okay, I've reduced the size of this air block. Okay, and I have to apply air, right? So add to the component. Okay, I apply the air block, okay, and we take the value of 1 to be for Young's modulus, Poisson's ratio, and relative permittivity of the air, okay, and then we simulate it again. So again mesh it and then go for the study. So it will take some time. I hope it depends on the how fast the system can process, and also we have not taken the higher mesh, the fine mesh, right? It is a general normal mesh we have considered. So I hope it will simulate faster. Have you all received any email from the iSTEM regarding your download of COMSOL software? Anybody? Have
Not
you?
yet.
Not yet?
No.
How many of you have is there many students who have applied for it? Anyone who has received the iSTEM reply from the iSTEM for the download COMSOL software? Anybody?
No, madam, I have not registered.
Okay. Anybody who has
Today I will do, madam.
and received? Anybody who has registered and received? Please raise your hand. Registered, not received. Can you please raise your hand? Okay, good. Sir has received. Okay, those who have not received, please write an email to them requesting for the access. So they will respond to it. Okay, because this is most important to practice. Because as we go ahead, the next session will be on how to design the MEMS accelerometer, keeping one concept of the cantilever beam, wherein we can understand how we can design this beams basically, or the stiffness. The other one is the concept of the this electrostatics. Okay, so it is taking some time. There it is showing error. Sometimes it gives a tolerance error between the elements. So see here, this is the displacement, and see what is the capacitance value, 10 to the power of minus 14, right? 1.21 into 10 to the power of minus 14. So we are expected to get the capacitance in the form of femto picofarad. Okay, femto to pico. When we design some sensor, it is good if you get the better capacitance value. So we need to consider that it should be done in the air medium so that we get the actual capacitance for the sensor. So this is the static capacitance. Okay, or we can say that when you apply a pressure of 1 Pascal, this is the static capacitance of 1.21 I am receiving or I am observing from my sensor. You can just put a 0 and find out what is the capacitance. And one more thing to know is, or to all of you is, it is important to know what is the static capacitance from the simulation. And since the displacement values are very small, in the nanometer scale, you may not observe the change in the capacitance because it is restricted to the 2 points after the decimal, right? Two values. So you may not observe much variation in the capacitance plot because of this constraint. Please, all of you, please remember that can be calculated with the help of hand calculation. We know the equation C is equal to epsilon A by D. So with the help of this equation, we can include the value of what is the change in the displacement, and that can be inserted in your equation, and you can find out the change in the capacitance, that is delta C. Okay, this is one more point to remember, because the values are restricted to 2 points after the decimal. That is the only reason why you'll not be able to see the change in the capacitance. Okay, is the Is the study clear to you? Is the flow clear? Anyone?
Yes, ma'am.
Anyone having doubt with respect to this, the flow? So basically a simple capacitive sensor, which is developed with the help of two physics, that is electrostatics and solid mechanics, which is coming as one module under the structural electrostatics. Sorry, electromechanics. Okay, electrostatics and solid mechanics together as electromechanics, which is under the structural mechanics physics. Okay, so
how to plot the graph here?
How to plot the graph?
Yeah.
In terms of
yeah.
this, you're telling this?
Yeah. Displacement versus voltage,
Yes,
capacitance.
yes. Yeah. That has to be. You can use either manually where you can have a table, and then that
It's
can be
not possible
plotted.
by tool itself.
We
By
can
giving
create
the points
yes,
from your
by
here.
creating a parameter list. We can get the in the table form here. We can get in the form of table, but provided you are going to give as a parameter. Okay, so under you can see under global definition, you have a parameter. So you have to define that variable pressure or the force as a parameter, and then that name has to be provided here as under the boundary load. Okay, the force. Then you have to simulate. Then you will get the complete table. Variation of the pressure with respect to or the variation of displacement with respect to the applied pressure or force. That is possible, but the thing is most of the time calculating if it is 1 pascal 2 pascal it is fine, but if the force or the pressure measurement depends on the structure, right, then it is not possible. Okay, fine. In that case it is not possible. If it is linearly varying, then it is easily you can define under the parameters, and you can do a parametric study. You will directly get the table, and then that can be plotted in the using Excel or Origin. Okay. I hope this flow is clear to you, right? So
Ma'am, I have one doubt, madam.
yeah.
Madam, if I'm wrong, please correct me.
Yes, please.
Actually, when you connect the ground to the bottom plate,
Yes, sir.
I think you have selected the top surface of the bottom plate. Am I right, madam?
Yes, I have selected the top. It is one and the same, sir. It is like once we fix that, even the bottom plate I can consider as fixed, and entire thing is fixed, the entire surface. So entire object is fixed there.
Okay.
But for our feasibility understanding, we do that.
Okay, but in the bottom plate, in the top plate for that positive charge, you have selected the bottom surface.
Yes, sir, because they are the one which are facing each other to store the charge or to find out the effective capacitance.
Okay, madam. Okay.
So that is the reason we have chosen that way. So if we compare the structures, as I said, MEMS capacitive sensor or the gyroscopes, basically it has extension like a springs. So the springs are connected to the mass, and they are united. So it is like if I choose one plate as a voltage, then the entire structure is taking as voltage.
Okay, madam.
So likewise. So it is for our convenience that it is our convenience to understand it. We have done it that way because they are the ones which are effective in measuring the capacitance. It will be directly electrode, sir. So altogether it is one electrode, right? So irrespective of wherever I give the ground, entire metal electrode is a ground. So that is a concept. For our understanding, I just took as the surfaces.
Okay.
Okay. Any other doubt? Any confusions or any clarifications? Yes, Sandeep, sir.
Ma'am, as sir mentioned,
Yes, sir.
if we apply the voltage on the top side of the top plate, will that make a difference, or it will
No,
not be an issue?
it will not. It will not. It is same because it is basically a conductor. So it is not at all necessary that I apply on the surface. I can bottom plate. I can also apply on the surface because basically they are the electrodes. So applying one phase, the other phase will conduct. So just for understanding, I just showed it that way. You will
Okay,
get
thank
the
you.
same. You will get the
Thank you.
same value, sir. Yes, sir.
Thank you.
Any other doubts?
Hello. Hello. Hello.
Manpreet.